C1, gravity near Earth. Near the Earth's surface is what we're talking about here. And we have our equations from before, which I like to write as D. This is kinematics, V naught T plus 1/2 AT squared. Remember the D is X minus X naught. And then here V is V naught plus AT. And then D is 1/2 V naught plus V times T. And then 2AD is V squared minus V naught squared. So these are the equations. This one has no V. This one has no D. This one has no A. And this one has no T. So we're going to apply this where the acceleration is due to gravity, which is 9.8 meters per second squared. And we're going to designate this with the letter G, little g. And I'm going to have little g always be positive. This one here, A, it depends. If you pick up to be positive, then you'll have a minus g. If you pick down to be positive, then you will have a plus g because you're going with the gravity, you're accelerating downward. So two observations at this point, that 9.8 meters per second squared is not exactly the same everywhere in the world. Depends on your latitude, longitude, depends on material inside the Earth, densities. A lot of things go into that. So for Asheville, there's this calculation that you can do with the National Geodetic Survey of the National Oceanic and Atmospheric Administration, NOAA. And when I plugged in my values, I got for Asheville 9.79 meters per second squared. And most books go at 9.8. Sometimes you will see 9.81 because if they look at some typical value, it's 9.8 like 06 or something, and you'll see this. I prefer not to do that and just go with 9.8 since the locations, will vary. So now in science, one of the important things about science, we talk about the scientific method, is to have theory and experiment or observation agree. So what I'm going to do is I'm going to hold a ball, actually it's a little ball of rubber bands that were put together in the ball, and then I'm going to drop it, and I'm going to time it by video analysis, because this happens very, very quickly. So here what we do is if we take, let's go back to general equation where you put z for the x and have this equation here. So I wrote out here everything with x and x naught, for example. And then here, if you if you drop the ball up here and you call this a z naught, say is equal to 0, we're going to start there and go down as positive. Then when we get down to the bottom, see, we'll have fallen this height h. So in other words, this is going to be 0, and it's then going to simply be, if you put a 0 there and you put an h here, and then this is a positive g since we're going with the g. So A is equal to g. We're using this case here. And then 2h equals gt squared, and then 2h over g is t squared, and then t is the square root of 2h over g. Okay, now let's plug in the numbers. We're going to go, when I measured this distance, turns out to be, in this case, 1.96 meters. So this is going to be 1.96 meters. And then we're going to divide by the G, which is the 9.8 meters per second squared. Notice that here the units are going to come out right. The meters will cancel and you'll get seconds squared up top, and then take the square root, you'll get seconds. So when you work this out, everything comes out nice, 0.63 seconds, which will go with 0.6 seconds, one significant figure. Now to check this theory, so this is basically theory, and we want to check with the experiment. So here we have the experiment, and this is the video of the ball being dropped. So here's the ball up here. It's going to fall down there. That's your 1.96 meters. I'm a little less than 2 meters, and I'm going to put it up over my head somewhat. So here what we're looking at is, when you look at the video, it's a little bit hard to see this, but this is saying 28 seconds into the video, frame 10. So that's frame 10. And then this one here, we're essentially on the ground. So we're hitting the ground close enough. There's going to be a little bit of experimental uncertainty here, but that's very, very close. And this one says 28 seconds into the video, frame 28. So that means the time corresponds to 28 minus 10 frames would be 18 frames. All right, now if you have 18 frames, we're shooting that video at 30 frames per second. So if I want to convert 18 frames to seconds, I use my conversion tricks where I want frames down here. So frames cancel, and then I get seconds. So now I have to fill in here to make this unity. So this is equal to 1. Doesn't change intrinsically what we're evaluating, just changing units. So that's going to be 30 of these frames for 1 second. That's the idea there. So you could write this as 30 frames equals 1 second, and then here I divided both sides by the 30 frames. So this is going to, cancel out the frames, and you'll have 18 over 30 seconds, and this reduces very nicely without a calculator. 3 goes into 18 6 times, 3 goes into 30 10 times. So that's 0.6 seconds, and that's what we got, 0.6 seconds. So this shows that the experiment and the theory agree, and that's very, very important in science.